very short presentation of this third webinar in the framework of Change2P Work Packet 2, which is led by Shineka. And this presentation in particular is done by Rohit. So he's a research software engineer at Princeton, Institute for Computational Science Engineering. He specialized in parallel CPU, GPU, distributed computing, MPI. And the very interesting topic for this presentation is currently is working with Prof. Jerome Trom to port the entire SPECFEM family of codes. So not only SPECFEM 3D that we already know in the CHILS project, to exascale machines using Kokkos performance portable library. So this is really interesting for Work Packet 2 activity, and also for the CHILS project, and also another project like UBEX, for example, in which SPECFEM 3D is really a very useful and interesting course. So very good presentation in the framework of performance portability task of Work Packet 2. So I'm very glad to have this talk from Lloyd. So good morning or good afternoon for us, and the floor to you. And thanks again for this talk.
Thank you, Piero. Yes, today's so I'm Rohit. Yeah, I work with on SPECFEM, but today's presentation is mostly about Kokkos. I'll give at the end a slide or two about the performance results that we've been seeing in SPECFEM, and specifically SPECFEM 2D, because that's the code that I've been focusing on for now, before we move on to SPECFEM, before we get some user feedback and move on to SPECFEM 3D. But as I mentioned, today's presentation is mostly about Kokkos, and in particular, I want to address like who should use Kokkos or why you would use Kokkos at the end of the presentation. So before we start, what is Kokkos? So Kokkos is a C++ performance portability library. By performance portability, I mean, firstly, portability. That is, you can write a single source implementation using C++ that can run across CPUs or GPUs. And by performance, I mean, you can get the performance most of the times, many times, as close to using native vendor-specific programming languages like CUDA, HIP, or DPC++. It has a more descriptive model compared to CUDA, HIP, and DPC++. That is, you can express your parallelism at a more higher level, which makes the code more readable and maintainable. You can compile the code for CPUs or GPUs, as I mentioned. And it also uses hardware-specific compiling tools. So if you consider something like DPC++ or SYCL uses its own compiler for compiling towards NVIDIA GPUs, for example. Kokkos, on the other hand, does utilize vendor-specific compiling tools. And in terms of MPI plus X frameworks, Kokkos is a shared programming model. That is, it works in conjunction with MPI. There is no MPI support for it. So if you think about MPI plus X, then one of the X's could be Kokkos. With any new, relatively new, because Kokkos was envisioned in 2013. With any new package like this or programming model like this, you think about sustainability. And in that sense, Kokkos has few plus points. That is, at least in the US, it has had a major buy-in across the Department of Energy labs and other national labs. If you think about major, widely utilized codes such as LAMPS, they have a Kokkos implementation. Trilinos, LAMPS is a molecular dynamics software package. Trilinos and PETC, which are mathematical solver libraries and widely utilized mathematical solver libraries, they also have a Kokkos implementation. There are over 100 projects using Kokkos. This number is at least a year old, so this is still a conservative estimate, but there should be more. So there are over 100 projects using Kokkos. The Kokkos team itself is contributing to the C++ standard. So many of the things that are part of Kokkos, for example, Kokkos views, which I'll go over later, would be part of C++ 23 as MD span. So many of the things that are in Kokkos would be part of C++ standard going forwards. And it also has an active developers community that you can access via Slack. So the outline of this talk is, first I'll talk about need for performance portability. Then I'll talk a bit about what affects performance, that is caching on CPUs and coalescing on GPUs, and how Kokkos achieves that with the help of Kokkos views. Then I'll correlate Kokkos threads, thread and memory hierarchy to CUDA thread and memory hierarchy. Then with that background in mind, we'll look at the question of why you would use Kokkos or who would Kokkos help. And finally, I'll give a slide or two about SPECFEM performance. So if you think about need for performance portability, if you think about the computing landscape right now, you have a bunch of GPUs, you have a wide variety of GPUs, that is, be it NVIDIA, AMD, or Intel, and CPUs as well, be it Intel or ARM. Each of these vendor-specific products have their own programming models, that is, CUDA for NVIDIA, HIP for AMD, DPC++ for Intel. If you want to write an application that runs on all of these platforms, then you need to write an application in each of these vendor-specific paradigms. This in itself is not an archaic problem. This is a problem that we are facing right now. So if you think about pre-exascale era machines, if you think about Oak Ridge itself, Oak Ridge had its pre-exascale era machine as Summit, which used NVIDIA V100 GPUs. And now let's say in the same lab, you want to move your application to the exascale era machine, which is the Frontier, which uses AMD GPUs. To be able to run that same application on AMD's GPUs, now you have to port it using HIP. And that is the process many people are facing right now, with Frontier access being given to many people. But the porting part itself is a very time-consuming problem. So if you think about a typical application, HPC application with 300 to 600 lines of code, and let's say porting requires only 10% of the rewrite of the code, and a typical software engineer writes about 20K lines of codes a year, then you're thinking about 2 to 3 years worth of software engineers' time just to port the application towards one specific vendor-specific hardware. If I think about SPECFEM 2D, 3D, and 3D globe is about 50K lines of code. And one of our collaborators that I work with, it took him about 18 months to port it towards NVIDIA GPUs, and about another 18 months to port it towards AMD GPUs. So all I want to say here, performance portability, like portability itself, is a very hard problem, and it is very time consuming. The option here is to use portability option. That is, either use OpenMP or OpenACC5. But if you use, so the common ones are OpenMP 5 and OpenACC, but if you use them, it's very hard to optimize for performance. So let's talk a bit about performance, or what affects performance. So let's take a typical example that we see in scientific computing, that is a matrix vector multiplication. So I have an A matrix over here multiplied by an X vector, and I store the result in Y. The serial implementation would look something like this. So I have double for loops. I'm looping over every element in A, multiplying the value to X, and then storing it in Y. Let's say if I wanted to parallelize this, the most naive way of doing that would be I parallelize the outermost loop. So essentially every thread gets a single row. And then it does its it computes the value for it. Every thread computes the value for its row and stores it in its corresponding Y location. Now, the performance of this application depends on how the data is stored. By that, I mean how the matrix is stored. So let's look at the two formats of storing matrices, the two major ones of storing matrices, a row major format or a column major format. In a row major format, I store the rows consecutively in memory. So I store the first row, then the second row. In a column major format, I store the columns consecutively in memory. So now let's look at a CPU running the matrix vector multiplication problem on a CPU with a row major format. So here I have a schematic of a CPU or a 4-core CPU with every core with its L1 cache. Now, the way threads are assigned to a CPU is that every thread gets assigned to a core, and it works independently of the other threads. Now, in iteration 1, I equals to 0, thread 1 will ask for its first element, that is a of 0, 0. But because of the way how cache lines work, rather than loading a single element, you would roll n consecutive bytes, where n being the size of the cache line, into the L1 cache. So in the next iteration, when I equals to 2, where that is when core A of the first thread asks for a of 0, 1, it already exists on the L1 cache. So a request is not being made to the DRAM. So essentially, by having a CPU running the matrix vector multiplication problem on a CPU with row major format, you're optimizing for bandwidth. Similar is the case for core 3. That is, thread 3 will ask for a of 2, 0. And again, rather than loading a single element, it loads the first n elements. And in the next iteration of I, when core or thread 3 asks for a of 2, 1, it already exists in the L1 cache. So you're optimizing for bandwidth. Now let's consider the case of a bad performance, that is running on a CPU with a column major format. Again, let's go to the same procedure. So thread 1 will ask for its first element, that is a of 0, 0. But because how the cache lines work, rather than loading a single element, it will load n consecutive elements. But these sequential elements are stored in column format. So it will load n sequential elements in the first column. Now, in the next iteration of I, when core 1 asks, or thread 1 asks for the second element, that is a of 0, 1, it does not exist in the L1 cache. So a request is being made to the DRAM. So essentially, by having a column major format for a CPU, you're not getting the best bandwidth. I see a question in the chat. Maybe. Oh, sorry. Thank you. So in the case of CPUs, you see good performance with a row major format. Now let's consider the same with a GPU. Before we do that, let me just talk about how GPU kernels work, or how work gets assigned on a GPU. So if you've written a GPU code or written a CUDA code, for example, then you know that the threads are bunched or distinguished into a grid of blocks and a block of threads. Each block gets assigned onto a streaming multiprocessor on the GPU. And each of these streaming multiprocessors shares a global memory. At a more granular level, if I think about it, if I think about a block itself, then a block contains a bunch of threads. And each of these threads are grouped into a group of 32. And that group of 32 is called a warp. Now, every thread in a warp, that is, every thread in a warp executes the same instruction at the same time. So the scheduler needs to make sure before any thread in the warp can execute instruction, all the data required by all the threads is available in the GPU cache. So the key takeaway here is that threads in a warp execute the same instruction at the same time. So let's consider the case of a GPU with a row major format. Again, thread 1 in the first iteration will ask for A of 0, 0. But before thread 1 can execute an instruction, the scheduler needs to make sure that thread 2 has its data. So this GPU is going to make a call to the DRAM again to get A of 1, 0. So essentially, by having a row measure format, you are not utilizing GPU cache. Now, let's say if we consider the column measure format, and similarly is the case for thread 3. So essentially, before any instruction gets executed on the GPU, a call is being made 32 times to the DRAM by having a row measure format. Now let's consider the case of a column measure format on a GPU. Thread 1 will ask for A of 0, 0 or its element. And again, how cache lines work, rather than loading a single element, it will load n sequential elements. Now, when thread 2 asks for its element, A of 2, 0 or 1, 0, it already exists on the GPU cache. So a call is not being made to the DRAM. So by having a column measure format, you're optimizing for bandwidth. So if you think about it, CPUs require a row measure format that is in 2 dimensions. If I think about an n-dimensional array, then the nth index, that is the last index, needs to be continuous in memory. That is what is called layout left in terms of Kokkos. And GPUs require a column measure format, or if you think about an n-dimensional matrix, then I1 needs to be continuous in memory, which is called layout left. In more performance-related terms, a row measure format or layout right on CPUs result in data caching, and a layout left on GPUs result in data coalescing. Now, this can have significant effect, like having the right data layout for a specific architecture can have significant effect for performance. So let's consider the case of a vector matrix vector multiplication problem. So rather than just doing a matrix vector multiplication, I'm pre-multiplying the result by a vector, and the final result is a scalar. So what I have here is on the x direction, on the x-axis, I have a number of rows. And note here that the total number of elements in the matrix is constant. So m times n is constant. And on the y direction over here, I have bandwidth. And if you can think about bandwidth as amount of data processed per second. The dotted lines show coalesced or uncached accesses, and the solid lines shows cached or uncoalesced accesses. I have 3 different hardwares over here. The black is for Haswell architecture, which is a CPU. The blue is Knight's Landing, which is again a CPU. And the red is Pascal 60, which is the GPU. So what you see here is that on CPUs, you have really good performance for cached accesses, that is the solid lines. And on GPUs, you have really good performance for coalesced accesses. And in the worst case, you see about a 6-fold difference in cached and in coalesced versus uncoalesced accesses. So most of the time, when you're compiling a code or like running a code, the target architecture is known at compile time. That is, you can compile a code for a particular architecture. So essentially, the data layout needs to be known at compile time and not at the developing phase. So, and the way that Kokkos does this is with the help of Kokkos views. So Kokkos views are multidimensional arrays. They can reside either on CPUs or GPUs. If they reside on a GPU, then you can create a mirror of it on the CPU and then sync the data between the two using deep copy. The view layout can be specified at compile time. That is, and the default behavior is to optimize is based on the execution space. So if you're running your code on, if you compile your code on the GPU, then the default is layout left. And if you compile it on CPUs, the default is layout right. But you can override the default, as I'll show you in the next slide. Finally, again, like layout left means column major format and layout right means row major format. So let's look at how a view is defined. So view is a templated class. By having a templated class, the template parameters itself need to be defined at compile time. So if you think about this view itself, this is a two-dimensional view. That is the two asterisks over here, the double star, define that it's a two-dimensional matrix, specifically a two-dimensional matrix that is defined at runtime, that is dynamic allocation. At compile time, I tell it that it is a layout left matrix and it exists on CUDA space, that is, it runs on a GPU, specifically NVIDIA GPUs. Finally, I name my matrix A and give it a tag. The tag is important for debugging purposes. And then at runtime, define what the dimensions are. So up until now, so by having this a templated class, you again, like you have defined what the layout dimension at compile time. So up until now, we've talked about how data layout can affect performance. But a key thing about if you've written code for GPUs, another aspect why GPUs are really fast is because it gives you control over thread and memory hierarchy. So if you think about how kernel execution works, then the GPUs or like CUDA gives you access to CUDA thread hierarchy with the help of CUDA blocks and the block dimensions, that is in Y and X. And it also gives you access to memory hierarchy, that is shared memory, which has really fast accesses compared to global memory, and texture memory, which has really fast accesses for random access. Kokkos also gives you APIs to access these GPU-related thread hierarchy and memory hierarchy concepts. So if you think about it, a CUDA block maps to something called Kokkos teams. A block dimension Y maps to something called Kokkos thread range. A block dimension X maps to something called Kokkos thread vector range. Shared memory maps to Kokkos scratch space, and texture memory maps to something called random access memories. The reason for utilizing these is that under the hood, when you're compiling for a CPU, this is a GPU-specific concept, but when you compile it for the CPUs, Kokkos has abstractions of these for the CPUs as well. So in the case of Kokkos teams, you're launching n number of teams, and within that, n number of threads. And within that, you launch another n number of threads, or team thread range number of threads. So with all of this in mind, let's now look at the question of why you would use Kokkos. So to do that, I'll have to compare it against the other paradigms that we have. That is vendor-specific programming languages, CUDA, HIP, or TPC++. Other portability options such as OpenMP5 and OpenACC, and Kokkos. So firstly, let's consider portability across architectures. The vendor-specified languages do not give you portability. You need to write separate kernels for every architecture, obviously. OpenMP5 and OpenACC does give you portability with the help of pragma-based approaches. Kokkos gives you portability with the help of Kokkos functions. In terms of performance, you can get optimal performance using vendor-specified languages because it does give you very low-level abstractions of the hardware. With OpenMP5 and OpenACC, it's tough to optimize for performance because it does not give you control over the data layout. Kokkos, on the other hand, you can achieve a really good performance or close to optimum performance by using figuring out, or like by making sure that the data layout is optimal. The cost, if you think about cost of portability, that is how much time it takes to port a code for a particular architecture. With vendor specified languages, the cost of portability is very high. With OpenMP5 and OpenACC, because you need to write different kernels for different architectures, obviously. With OpenMP5 and OpenACC, it is very low. If you have a code that is running on a CPU, for example, hopefully you can easily port it with the help of by sticking pragmas on top of your most compute intensive for loops. Kokkos, on the other hand, I'd still say the cost of portability is pretty high because you need to analyze what are the bottlenecks in your code and how your data still needs to be laid out and how it maps to different architectures. The cost of maintenance, on the other hand, with CUDA, HIP, and DP6++ is still pretty high because with every newer architecture, you need to make sure that your kernels are optimized, or if they're not, you need to fine-tune them. With the help of OpenMP5 and OpenACC, the cost of maintenance is still very low because you're assuming that the compilers are doing a good job of implementing the standard. In terms of Kokkos, I'd say the cost of maintenance is very low, assuming that the Kokkos backend is always optimized for that architecture. With respect to compiler dependence, OpenMP5 and OpenACC are standards, and vendors have the flexibility of how they implement the standards. And with respect to Fortran binding or Fortran support, OpenMP5 and OpenACC is the only one that you can use, that you can port for Fortran. You can use CUDA, HIP, or DPC++, but with the help of C++ binding, and same thing for Kokkos. Now, let's say if you want, like with all of this in mind, when is the time you would use Kokkos? So if your goal of your application is to achieve really good performance for all architectures while keeping the cost of maintenance very low for future architectures, that is where Kokkos shines. If the goal is just to run a code just to port a code towards a GPU and a very specific GPU, and you do not care about performance as much, then OpenMP5 and OpenACC might be the option for you because the cost of portability is very low. But if the goal is to get very good performance while keeping the maintenance for future versions very low, that is the time when Kokkos shines. Now, lastly, I want to talk a bit about SPECFEM performance. So again, like reiterating, the application layer is SPECFEM. We are using Kokkos and C++ to port it. So essentially, I'm porting the whole software package from Fortran to C++. And then we compile it for different architectures. What I have on the right here are two plots, one for GPUs and one for CPUs. On GPUs, we are comparing the SPECFEM baseline performance is SPECFEM performance running on NVIDIA GPUs, specifically NVIDIA A100s. And the black triangles are SPECFEM Kokkos performance, that is the ported code, running again on NVIDIA A100s. On the x-axis, I have total number of spectral elements. The first y-axis is runtime in seconds, and the second y-axis is performance related to the CUDA kernel. What we see here is that the SPECFEM Kokkos performance, at least on the GPU, is very close to the current SPECFEM performance. So we see only a 6% degradation in performance when using Kokkos. On the case of CPUs, rather, we do see a large degradation in performance. That is, the current SPECFEM, the Kokkos version takes twice as much time as the baseline version, the current SPECFEM. The reasoning for that is it's very tough to, at least for the kernels that I'm working with, or like finite element kernels, to be frank, it's very tough to optimize for vectorization while getting really good performance on the GPU. And our goal was, or after speaking to Yaron, the GPU code would, most of the times, GPU code would be the production code. So our goal was to optimize it for get the best performance as possible on a GPU. and then get a good performance on a CPU. So essentially, we kind of sacrifice on the CPU. We could have gotten something in median by restructuring our code a bit. The inset here, which is very small, shows the scaling law with the number of threads. So essentially, I want to say with using OpenMP, this is running on a single node. So what we see here is linear scaling or like inverse scaling as we increase the number of threads. So with that, I can take any questions.
Thank you very much. Very interesting. Maybe I see some question on the chat. And
Okay, I can look at it. Cost of portability. So the question is cost of portability from Antoine. The cost of portability is the cost of porting from something else to Kokkos OpenMP, not the cost of porting from architecture to another while sticking in the same programming model, right? Yes. So the cost of portability, what I'm thinking is like, let's say if you have a CPU code, like a code that runs, and you want to port it towards a certain architecture, that is what I call the cost of portability, not from one architecture to another. From one architecture to another is what I call cost of maintenance, if that makes sense. I see Ranjit has a question.
Yes, are there other options other than Kokkos which do similar things? Are there other libraries which do similar things?
Yes, that's a really good question. Currently, the competitor to Kokkos is something called Raja. And Kokkos is developed by Sandia National Labs. And whereas Raja is developed by Lawrence Livermore, I think. Lawrence Livermore or Lawrence Berkeley, I get confused between those two. But it's a very similar, what I'd say is that it's a very similar performance model or like very similar architecture. And going between the two is personal choice, I believe. The reason we went for Kokkos is the support or access to the developers if you have a question or performance related issues is very easy. So because they have a Slack, you can easily ask them questions. I'm not sure, in that case, I'm not sure about Raja, but Kokkos and Raja are very similar to each other.
Okay, one follow-up question. So for those of us who are hardcore Fortran programmers, is the message to learn C++ and move to C++? Is that the message that is coming across?
Not, to be frank, like in a sustainable point of view, if you go for Kokkos or Raja, then yes. But if the goal is to just port your code, then you could use Fortran bindings. Kokkos, here I've been talking about view layout and things like that. But Kokkos still gives you access to have unmanaged views. So essentially, you give access to Kokkos where your data is laid out via a pointer and not let Kokkos manage the data, but still be able to use Kokkos API. So you don't get access to the Kokkos data layout features, but you get access to other portability features like using CUDA blocks, for example, using Kokkos teams. So depends on the use case. In the long term, if I would say like, if the development is going to continue for a while, then yes, at the end of the day. But if it's just one small project, then probably not, because the cost benefit analysis might be not worth it, if that makes sense.
Okay, thank you so much.
Yep. I see we had one more question. Can you comment on Fortran binding?
Yeah, this is senior.
Yes. So not really. So with Fortran bindings, for example, you still will be able to write Kokkos code. So at the end of the day, you are writing C++ code, which you call under Fortran. But the only access that you lose is, as I stated, is the access to view layout. Because now by having Fortran bindings, your data in memory is laid out by Fortran. So Kokkos does not change that data layout. It just wraps it with a view class. So you can use the other portability APIs from Kokkos, like Kokkos Teams, Kokkos Thread Range, or like other Kokkos range, for example. So essentially, you only lose view layout. So I wouldn't call it. It adds a huge huge complexity. If you're doing similar thing with CUDA, it probably is the same.
I think there is
Yeah.
another question on the chat.
So the next question is, what about evolution of Kokkos? What is the cost of upgrading between version of Kokkos? So I'll initially talk from what I've heard and my experience as well. So apparently, like from Kokkos versions 3, like earlier in the development phase, there were issues with API changes, especially like in the very early versions in 2018, 2019. For now, I've not seen many changes in the API. So the cost of upgrading essentially is changing which version of Kokkos you want in a CMake file. So it's very minimal. And they do not, most of the times you don't need any rewrite of your code unless they deprecate some features, which in minor cases have been true. Hope that helps.
Okay.
Yeah, I
other
have a question.
questions?
Yeah, I have a question, maybe from very interesting. But most on the perspective of the Center of Excellence and the SPECFEM evolution. So, what is, in your opinion, the SPECFEM roadmap? So basically, for what I understood, the idea, at least from your side of development, is to port the family of codes to C++ and then using Kokkos or an alternative performance portability layer. Do you envisage that this is the final decision, or in order to have maybe one line of development of the codes, or there are still some possible alternatives? So, for example, that can be based on top of the Fortran layer. So the roadmap is already selected from your opinion, or there is still chance to have some alternatives?
Yes, so for now, like we are going forward with the C++ version. But to be frank, like the Fortran versions will still be supported. I see this as a transition. So C++ development works in parallel with the Fortran development. So the current Fortran versions, the SPECFEM 2D, 3D, and 3D Globe, for example, would stay the same. Daniel, who is the maintainer, will take care of maintaining it and adding new features as they come by. The C++ version development works in parallel, because I see, for example, in the end, I do see a synergy between those two, because many people are using Fortran, and like as architectures or like as the computing landscape evolves, at the end of the day, I do see the C++ version to be faster. Having a C++ version gives us more flexibility in terms of implementing new features as well that we do not have in our Fortran code. For example, adding fault mechanisms is very tough in the current Fortran version, which could be easier in the C++ version, just because of polymorphism and implementing using classes. And it's not like the Fortran versions, you cannot do that in Fortran, but at the end of the day, this is a code that was developed in '99, and additions were made to it over years. So, and over generations of graduate students, generations of postdocs and faculty. So adding new features and understanding the code is very tough for newer people coming into the code, into the community. So that is the reason we see that the C++ version to be the future roadmap, but it will work in conjunction with the Fortran version for now. But as new features get implemented and those features become popular, I do see people switching over. And the goal is to hide the parallelism so that from the domain scientists, like as much as possible from the domain scientists. So if you want to implement physics, then the goal is to have an abstraction where you can just implement the physics and let Kokkos or the driver class in C++ take care of the parallelism so that it's easier to implement new features. So those things like that is tough to do in the Fortran version without completely re-architecturing the code. And if we are re-architecturing the code, then why not re-architecture it in C++? One of the initial conversations with Yaron, he mentioned that him and Dimitri, when they decided on Fortran, was because at that time, the performance of Fortran was significantly better than C++ because of compilers. But compilers over the years have gotten better. So you do see similar performance now.
Okay. Thanks for, yeah, very intense answer. Yeah.
Thank you.
Any other questions? No, I don't see any hands. Okay.
You know what, I just want to step in to thank the presenter for this very nice seminar. It's been very clear, so thank you very much. And
Thank you so much.
time and
Thank you for inviting me.
a virtual applause for you. Thank you very much.
Thank you so much.